Hello, we are a sub-team of Team AI Ramanujan, consisting of Josh Lee, Brandon Wang, and Hyun-Sang Han. Srinivasa Ramanujan was an Indian mathematician who was famous for producing highly non-trivial mathematical equations. One of these equations is seen on the right side. Unfortunately, most human beings can't find these relations naturally, so what should we do to find these relations? Naively speaking, searching for mathematical propositions is like finding underlying patterns. Unfortunately, this can't be done without rigorous training. So instead, we use artificial intelligence. Automatic translation is one of the most important applications of natural language processing. What if we apply automatic translation to mathematical expressions? The first person to suggest this method was Professor Shamos. First, he generated a large body of mathematical expressions and their combination, and then he evaluated each expression up to 40 digits below the decimal point, and considering these values as bins, allocated each expression to the same bin. If two expressions were located in the same bin, possible conjecture would be induced. The four expressions in this slide are not only in the same bin, but are actually analytically equivalent expressions. Let us see how this actually works. This is part of Professor Shamos' dataset. As you can see, there are two different expressions allocated to 3.1482, etc. Through this observation, we make a conjecture that these two expressions are actually the same. There was also another dataset of mathematical expressions which we could use. It is created by a Canadian mathematician named Simon Plouffe and contains much more data than Professor Shamos' dataset. But the main drawback is that it is not in Mathematica but in Maple, and conversion is required. Also, there is a problem that the decimal points are randomly located. So why would we use a neural model and not use a rule-based model instead? While a rule-based model is tempting, there are two major drawbacks. First, mathematics as a language is ever-changing, and like many other languages, it needs updates. So we can't really expect to find a good rule that will universally apply. Also, we will need to fine-tune the results according to their evaluation, since it is almost impossible to generate two distinct mathematical expressions that are both syntactically correct and also have similar values. We should focus on the first goal of matching the syntax and then fine-tune the result so that they go to the same value. The whole team consists of 14 people, including the two professors. While our team was big, our goal was even bigger, so we divided the general task and assigned different tasks to different teams. The smaller team, consisting of Josh, Brandon, and Hyun-Sang, embarked on the generation of formulae. For our baseline model, we select GPT-2 for text generation. And GPT-2 basically contains the decoder portion of the transformer structure. It is trained with the generative pre-training objective, meaning that given a text corpus, it is trained with to predict the next token, given all previous tokens. The baseline model we select contains 12 layers, each containing 12 attention heads, for a total of 142 million parameters. The first problem of our generated dataset was that it lacked diversity and the same tokens kept appearing. This indicated overfitting caused by lack of data. To solve this problem, we had to use Plouffe's dataset, which contains 40 million expressions. Another problem was that the generated expressions didn't often have the same number of left and right parentheses. To evade this issue, we introduced a prefix notation, also known as the Polish notation. Polish notation doesn't require parentheses at all, and an example of its application is like the example written below. In the generative adversarial network model, we incorporate a discriminator module whose role is to decide if a piece of data is synthetic or authentic. Because our model is struggling with data not conforming to standards, we feel it would be pertinent to experiment with the GAN architecture. Therefore, on top of the original generated module, we introduce a feed-forward network as a discriminator and perform policy gradient updates according to set GAN. So now, the objective of the generator is no longer to minimize the generation loss, but is to fool the discriminator. This approach has given reasonable results in image and text generation attempts. And here are the results. Although Polish notation is fundamentally equivalent to using parentheses, it yielded better results for our application and thus proved to be a fruitful attempt. Not only is it universally convertible to both Maple and Mathematica in both directions, but also we could build upon the other team's work. Our model was able to achieve very reasonable results. Each batch of results produces unique expressions that are sufficiently complex. The problem is that even with conversion to Polish notation, it was hard to consistently satisfy proper mathematical syntax. Formula generation is a very difficult task for deep learning network to learn. Unlike natural language processing, mathematics has very rigid rules on its syntax, structure, and usable parameters, and a single character out of place, such as an extra digit or a stray parenthesis, can completely alter the meaning and validity of an expression. Some further improvements are to express expression as a tree instead, making it easier to verify the expression structure. Thank you.